for staying with us instead of running to the lunch. Yeah, we'd like to present you something about ontology concepts and topological abstraction of infrastructural networks. I'm head of research for A+S. We are a company which is in Dresden in Germany, and yeah, we have two big points. On the one hand, we are planning infrastructure in road, rail, and also energy like power poles. On the other hand, we are a software development company, and we develop our platform Corfin, where the screenshots are taken from. And yeah, we are founded since 1998, and we do since then all those BIM models in one overall environmental model. For the project background today, the project background is called FlexiDAC. It is flexible digital systems for rail-based transportation in growth regions. And as you see here, it is located in Brandenburg near Berlin. Yeah, we have a look of what happens after coal mining stops in Germany. What do we do with the rail network there? And you see some parameters for that. We have a lot of tracks and a lot of crossings, signals, etc. And in that research project, we take a look what we can do with that infrastructure after yeah, coal mining has finished. So here are some basic project impressions from that project. One point here is a bypass for the Cottbuser Ostsee. It's the biggest man-created sea in Germany. And the idea is to reuse the rail network, which was used for coal mining, and make a bypass around the sea so we can do city development there. And second part would be, yeah, we take that and do cargo transports on that existing rail tracks. So, but we can also use that for testing, and one overall objective is from a partner in the project, the train dispatcher in the cloud, which we can test there. And therefore, we not only need the geometry, which you see here, we also need topology. And the topic today is how we link that geometry with topology, and then yeah, how we can continue using it. Connect geometry with topology. Okay, that's quite simple. We use directed graphs with nodes or vertices here and edges, and then we take a look what is the most simple layer there. And here you have a simple switch and a double cross switch, and that are not only one node, that are contained of multiple nodes. As you see here, you have a node to go inside, two nodes to go outside on the simple switch, and there are also exist edges between. And now that we call the micro topology, because you can't reduce it, and you have the exact connection to the alignment itself there. But what we can do is a topological abstraction of that, so we can build a macro topology. So you see, we summarize the entire simple switch to one node, and that means behind that one node you have a subgraph of the inner nodes of that. And but we reference it, and so after referencing, we still have the background to the geometry again. And that you can not only do for a simple switch, that you can also do for an entire station or for an entire city. So you can build parallel macro topologies based on one micro topology, and the micro topology is the ground you start from, and that is aligned to the real alignment, to the real geometry itself. So that is the stuff I was involved in. Yeah, the old school relational databases stuff. We create yeah, an SQL-like relational data model for that with a geometry stage on the top, then the micro topology stage and the macro topology stage, and we need some abstract topology so we can reuse it. And from that starting point, yeah, we continue, and yeah, now it's time for my colleague, Al-Hakam. You can continue with the cool new stuff.
Yeah, well, the concept that Jens presented in the previous slides could be realized using various technical solutions and data models. One possible solution would be a relational database. And yeah, when Jens presented his database and his solution to me, I thought, wait a moment, why don't we use an ontology for that? Because the OWL ontologies are also graph-based or have a graph structure, and therefore are also flexible to extend and modify, and they represent this infrastructure topology in a more native way, in my opinion. And one main advantage of using ontologies would also be to connect this infrastructure ontology to other domain ontologies like the building topology ontology or the rail topology ontology that already exists. And yeah, we decided for using the web ontology language, or in short OWL, since it is a supported solution due to being a V3C standard. And I mean, we are engineers from Germany and we love standards. So using a V3C standard seemed like a legit solution to us. And we thought, okay, yeah, my first initial thought was, okay, it's just some nodes and edges that are connected. Let's directly model this also in OWL. But the concept of Jens involved that also the edges need to be referenced by other nodes from higher level topologies, like from a node, for example, a station that is located or is defined in a macro topology and wants to reference an edge in a micro topology. And there are various technical solutions how to solve that. You can use RDFS star, you can use Neo4j, but I wanted to yeah, use a solution that is OWL based, and OWL and RDF star are not so good compatible in my opinion, so I used an array relations pattern. It's a common pattern used in ontology modeling, and therefore the edge is also modeled as an individual that is referenceable by the stations or the nodes in this case, and also can be referenced by nodes from higher hierarchies, and also you can add additional information to these edges. So it's a way to model this concept that Jens proposed in the previous slides in my opinion, good way in an ontology. And this is the result in the end. So basically we have three core components. We have the nodes, the edges that are connected with each other, and then of course the various topology instances. So you have not only one topology, but multiple, like several macro topologies and also micro topologies. And you can then, of course, inference node and edge relations. So here we have a simple example that a station connects to an edge, and this edge also connects to another station or node in this case. And of course, you can infer using a reasoning engine that also the inverse relations between the edge and the nodes are existent. And of course you can also infer direct relations between the nodes using property chain axioms. In the end we also added some subclasses for nodes and edges that classify nodes and edges as macro nodes and macro edges that belong to a macro topology, and we also have a specific type for nodes and edges that belong to a micro topology, or in our case we classified it as alignment topology. And the nodes and the edges, they are all topological elements and therefore classified using an appropriate class for it. Speaking of the alignment topology, this is a very important part of our topology. So this is the direct connection, or should be the direct connection to the geometry. In Corfin, in our software Corfin, we can represent sections and stations using these classes. And now I come to the conclusion. So we developed a multi-level topology concept for representing the infrastructure. This concept could be realized using various data models and technologies. Prototypically, we realized this using an ontology, but it's also possible to use relational databases for this. And in the future, we try to align it with other existing ontologies. What, in my opinion, is also very interesting is that the file ontology for geometry and ontology for managing geometry could be utilized for connecting the geometry data and files to our topology. And the last slide is for my colleague Jens.
Okay, let's make it short. You can use that also for roads. It's the same, or for power lines. It's interdisciplinary, and we want to connect domain-specific databases with that topology. That would be interesting. So contact us if you are also interested in, or if you have real data we can use for that. Thank you very much.